Hi, welcome everyone. This video tutorial is on explaining the concept of endogeneity and its severity by using simulations using Streamlit app. Before I start with changing the toggle menu, I will explain a little bit here. So I will show uh, how endogeneity comes, how it creates bias, how it changes the size and the power of the estimates, and then I will compare the OLS with instrumental variable regression. So I will start with the data generating process. So let's assume my residuals are random normal. My x variable is a function of residual and some eta, which is another term which will be explained later on. Okay, and then there's a theta term that explains the relationship of x with the u and the eta t, and then yt dependent variable depends upon xt plus ut, where the true slope of the variable is 1. We assumed in this estimation that it will remain 1. So if instrumental variable generation is enabled, then our zt will be actually equal to rho phi eta plus 1 minus phi square epsilon t. So that the correlation of z and u remains 0, and correlation x and t will be equal to phi 1 minus theta square. So this is the formula that are required to create data. So I will start with example where there is no endogeneity. So endogeneity is actually the correlation between the error term and the independent variable. And I will resume or turn off the instrumental variable regression. So I have a 660 observation sample, and I will only do 500 application in order to save time. And then the plot of the power plot, I will start with 0 to 2 value because our beta is 1. So I assume that it should be in between this range. Okay, you can increase the steps in order to make a smoother curve. So I can do 0.1 here. So I will run the simulation. It will tell me that my OLS is 0.99995 with beta this, with mean of standard error, and then empirical size. So we have uh, this information. Okay, we plot the beta distribution, and because the mean of the distribution is actually is where the beta exists. So it means there is no biasness because there is no endogeneity at the start. And the t statistics we saw it's normally distributed, and ideally it should be. Okay, so it compares a null hypothesis beta 1 equal to 1, and alternative is that beta 1 not equal to 1. So only very few observations are outside the outside, which will become, so ideally it is only 5%. Okay, next we saw the p-values, and they are falling. So only 5% of the only 2.5% of the p-values are so the p-values are rotating around 2.5% bin. Okay, so it means only few of them are less than that, means the means for the there is only less than 2.5% sample which is saying that beta is not equal to 1, and ideally that's good case because the remaining 90 um, 90 remaining 95% is saying that it is equal to 1, and because there's a two tail, so it's 2.5% showing here. Okay, 2.5% each. Now we see the power of the test. Power of the test checks us that is the ability of the test to recognize beta at a true place. The true place is beta equal to 1. So we found out that the p-value actually falls down, and it is less than 10% level at true beta 1. Otherwise, if you pick any other beta, the p-value is not less than the threshold. Okay, so this means that it has a true power to determine actual p. So endogeneity theta is mixed bias. So endogeneity theta is equal to 0 makes so these are some interpretation for the case of endogeneity. Okay, so tip is increase the theta to see a OLS bias explode, toggle instrumental variable and vary row size to visualize the bias variance trade-off. Okay, so what that is say is that when you increase the theta is here, it will increase the endogeneity and endogeneity bias. But when you increase the phi, increase the row value, it will make the instrumental variable able to control endogeneity, but it will also create other problem, which is bias variance trade-off. Means when you introduce an instrument which is very good, it will also lead to increase in standard error of the model. Okay, so let's start with the example. I will introduce some endogeneity. Let's say that my residuals and variables are correlated by this much. I will not introduce instrumental variable yet. I will do the simulation again. Now you can see it is different from 1 now. So it is not able to recognize the actual beta. Okay. Now if we make the distribution, you can see that it is uh, way of the line. Way of the line. So this is showing that there is biasness because of endogeneity. The actual beta is 1, but the estimates are showing somewhere 1.4. And when we test the hypothesis testing, so T's are somewhere here, but the actual T distribution should be here. It means uh, your model will be 100% rejecting beta equal to 1, means your betas will be not 1, but in reality it should not reject equal to 1. It means it will reject a true null hypothesis, but rather than it will accept a false alternative hypothesis. That's because of endogeneity. You can notice here, so this is the actual t values, this should be the ideal t values. So it means that if the beta equal to 1 was a true hypothesis, we will be rejecting it all the time in the endogenous regression. Then if you look at the p-values, you can notice that the p-values, uh, the empirical size, all of them are below 2.5%. It means they are rejecting all the time. So our estimates will say that beta is not equal to 1. So same thing here. So the power is also at a wrong place. It will try to estimate beta is equal to 1.4 at 5% level, but actually it should estimate at 1. So you can understand how much problem there is if there is endogeneity, and it only depends on the level of correlation. If I increase it, the problem will increase further. Okay, now what I will do is I will introduce an instrument. Let's say the instrument is only correlated 50%, half with the relevance is 50%. It is not fully relevant. So let's start with this. You can see the original problem is 1.4. It is away from 1, but the instrument, even though it is only 50% similar, it has corrected the beta. It has increased the standard error. It has also increased the standard error of the regression. Okay, now we go to C. So you can see the light blue color is the instrumental variable regression distribution, which is aligning near to the true beta, but it is more spread. It has corrected the bias, but it has increased the variance. Now, if you see the t value, you can notice that three values are there, and they are actually are able to accept null hypothesis at the correct time. So that's really good. Okay, now if you see the p-values, so the dark one is problematic, but the original one is with the line, so it should not go up like this. Okay, but it should stay with the line, so instrumental variable regression is fine. Now we see the distribution now. So light color, you can notice that there's still little bias here, but because the lowest p-value is somewhere where it is not in the middle, it's 1.03 because the instrument is not 100% correct. So what I can do, I can make it best possible. Okay, means the instrument is actually the true variable. So you can notice that the mean is correct, the standard error is corrected, it's not that big. So it's correctly distributed. It looks same as this, but at the right place. The distribution is right. The shape is right, and then you can see it's actually at the right beta. So this example highlights you how important is when you do an estimation, and then you need to make sure that if you don't check for endogeneity, and if there is endogeneity, how wrong the estimates are, and how you can have to uh, adjust it so that you can get the correct estimates. So the link of this the simulation I will share in the chat in the comments, so you can share it with your colleagues and so that they can use this case study for demonstrating the importance of instrumental variable regression. Thank you.